Welcome back to lectures on engineering mathematics 2. So, this is lecture number 43 on Fourier cosine and sine transform. So, today we will discuss what are these transforms. So, one will be the sine transform, the other one would be the Fourier cosine transform, and then we will discuss the properties of these transforms. Well, so consider the Fourier cosine integral, which we have already discussed in the previous lecture, and that was given as f x is equal to this 0 to infinity f u cos alpha u du and cos alpha x dx. So, this was the coefficient which we were denoting by a alpha in previous lecture, and then f x was integral 0 to infinity a alpha cos alpha x dx. So, and now we have just substituted that a alpha in this representation, the Fourier cosine representation. So, finally, we have this integral which we have assumed all a convergence. So, that this is equal to f x. So, that was already discussed in the previous lecture. Now, what we are doing, we are just breaking this 2 over pi into the product of square root 2 over pi and again square root 2 over pi, and then this part which is with this square root 2 over pi and this portion of this a alpha, we will denote that f c hat alpha as this is square root 2 over pi f u cos alpha u du. So, this portion we have given a new name, this f hat c for the cosine. So, c stand for cosine, and since this is a function of alpha, so we are calling it as f hat c alpha, and then once we have denoted this f c hat alpha, then f x would be square root 2 over pi and then integral here 0 to infinity, and then f c hat alpha, and then we have cos alpha x d alpha. So, this Fourier cosine integral we have with this new notation now f c hat alpha, it is defined as f x is equal to this square root 2 over pi and this integral for this where this function f c hat alpha is serving as its integrand. And now we can introduce, so this integral here, because it is transforming the function f to a new function which is a function of alpha. So, no more the u is there, u has been already integrated and we have a new function which is a function of alpha. So, this is called Fourier cosine transform of f, and since we are talking about the 0 to infinity. So, Fourier cosine transform in 0 to infinity, and the notation we use usually Fourier and c for cosine of f. So, whenever we are writing that Fourier cosine transform of f, as per this definition, this will be 2 over pi and then integral 0 to infinity f u and then cos alpha u and du. So, that is what we use this as a kind of operator or the notation we can consider for getting the Fourier cosine transform. Similarly, this term, because having this Fourier cosine transform, so this function of alpha, and then we want to get back to the function, the original function. So, this formula may be used, and therefore, this is called the inverse Fourier cosine transform of this f c hat alpha, and notation we use here, that is f c inverse of f c hat. So, this hat is used just to denote that this integral, now since it is a function of alpha. So, we are just naming it f c hat alpha, and then if this such a function of alpha is used here in this second integral and it is integrated over alpha after this multiplication of cos alpha x, then we will get this f x the function, and therefore, this is called inverse Fourier cosine transform. So, similarly we can also define the Fourier sine transform, and that exactly will be coming from the Fourier sine integral representation. So, this is for instance the Fourier sine integral representation. Again we have a similar split, and then this portion we will call at f the sine hat alpha, and then we can define the Fourier sine transform as well as inverse Fourier sine transform. So, Fourier sine transform is given by this integral. Now, we have this sine alpha u instead of cos alpha u, and f x. Now, getting back to f x, we will use again this Fourier sine integral representation. So, having this f s hat alpha, if we integrate after multiplication with the sine alpha over this d alpha, we will get back to the function f x, and therefore, this is called Fourier inverse transform. So, the first one we are here, and this is called Fourier sine transform. The notation for sine transform is f s f, and then for the inverse Fourier sine transform, which is given by this integral, and here the notation we will be using, that is f s inverse f hat s. So, we will discuss now some important properties of Fourier sine and cosine transform. So, the first one is the linearity property, which is a very common property of all integral transforms, including the Fourier transform later on we will see, and then the Laplace transforms, etc. So, let this f and g are piecewise continuous, absolutely integrable. So, all those conditions for the existence of such transforms. Then for constants a and b, we have this result. So, if we apply the Fourier cosine transform on this linear combination a f plus b g, so that will be equal to a the Fourier cosine transform of f, b into Fourier cosine transform of g. And similarly, for the Fourier sine transform, if we apply on a f plus b g, the result will be equal to a times the Fourier sine transform plus b times the Fourier cosine transform, and this result can easily be obtained just plugging this a f plus b g into the definition. And as we know now, it is an integral, and integral enjoy such linearity property. Therefore, all these integral transforms, they have this linearity property. The another one which is most important from the point of view that we will be using this derivative theorem for solving partial differential equations or other kind of differential equations, and there this derivatives, the Fourier transform of Fourier sine or cosine transform in this case of derivatives will be used. So, again if f is continuous and absolutely integrable on this, and we assume that f prime is piecewise continuous on each finite interval on this 0 to infinity, and we let that f x goes to 0 as x tending to infinity. So, we have this additional property of f which says that it must go to 0 as x goes to infinity. Then we have this nice result that Fourier cosine transform of the derivative f prime will be equal to alpha Fourier sine transform of f x, and then this is another factor with minus sign square root 2 over pi, and then we have this f 0. So, the nice property of this derivative which we enjoy for solving the differential equation. So, left hand side we have derivative, and when we are taking the Fourier cosine transform of derivative, the right hand side is free from derivative, and this is exactly is the point which helps us to solve the differential equation, because when we take the Fourier cosine transform for instance, then in the differential equation, so we get rid of the derivative term, and this is how we use Fourier cosine or Fourier sine transform for solving differential equation. So, similarly for Fourier sine transform, when we apply on derivative of f, then we get minus alpha times the Fourier cosine transform of the function f. This we can easily prove by the definition itself. So, the Fourier cosine transform for instance of f prime, as per the definition we can write down f prime x cos alpha x dx, and then if we integrate this by parts we will get the desired result. So, integrating this by parts, what we will have? We have here f x now, and then the cos alpha x as it is, then we have the limits, then this cos alpha x will be after differentiation sin alpha x with the minus sign, and there was a minus sign already in the formula. So, we have the plus there, and one alpha will also come as a result of this differentiation, and then we have f x, which is the derivative of this integral of this f prime. So, this is just integrating this by parts, and then we can use here, we can substitute the upper limit in f cos alpha x and also the lower limit. So, we have already discussed that, or we have already assumed that this f x goes to 0 as x goes to infinity. So, the upper part here, when we put this x to infinity, this will go to 0, and for the lower one we will get then f 0. So, using this definition of the Fourier sine transform in the second one, what we will get, the first one says when we put this 0 there. So, we will get this f 0 with the negative sign, and then the second one alpha, and as per the definition of the sine transform with this factor square root 2 over pi, this will become Fourier sine transform of f x. Similarly, the other results on this Fourier sine transform can be obtained just by integrating by parts. So, we are leaving that portion here. So, these are the steps basically which can be used again for Fourier sine transform. So, these above result can easily be extended to the second order derivatives. That means, if we apply the Fourier cosine transform on the second derivative, we will get minus alpha square with Fourier cosine transform of f x, and then there will be additional term here square root 2 over pi f prime 0. So, again this enjoys the same property, that when we apply the Fourier cosine transform on this f double prime, then we get the right hand side which is free from the derivative. So, we have only the Fourier cosine transform here, but there is no derivative, only the derivative here at a one point x equal to 0. Similarly, for Fourier sine transform we will get this formula. So, square root 2 over pi alpha f 0 and minus alpha square the Fourier sine transform of f x. Well, so, and again the assumptions what we have used for proving this Fourier cosine or Fourier sine transform of f prime, they are also extended here. That means, we assumed the continuity of f, and now also for f prime and piecewise continuity of f double prime, and then we have also assumed that f and f prime goes to 0 as x approaches to infinity to get these results. But these such assumptions are very obvious, which we will also observe during the applications to solving differential equations. Well, so we have also the so called Parseval's identity in this connection. So, if we have the Fourier sine and cosine transform, we have the following identities. So, Fourier cosine transform and Fourier cosine transform of the function g. So, we are considering two functions here f and g, having all properties for the existence of such transforms. So, the product of the two transforms here, when we integrate over this alpha from 0 to infinity, that result will be equal to integrating f x g x over this x from 0 to infinity. That is what we call here the Parseval's identity. And if we take here f equal to g in this left formula, basically we will get another identity, which is f c hat alpha whole square, because that will be product, and the right hand side will be also the product of the same function. So, f x whole square. So, this is basically the same identity. For the sine transform also we have similar results. So, when this product of the sine transforms is integrated over alpha, we will get this result equal to the product of this f and g integrated again over this x from 0 to infinity. And similar to this result, we can also write down for Fourier sine transform. The proof of these Parseval's identities can easily be done. So, we will take the right hand side of the identity f x g x integrated over 0 to infinity, and then we will use the definition of this inverse Fourier transform of g. So, which is square root 2 over pi, and then we have g hat alpha cos alpha x d alpha. So, this is what we are doing for the cosine transform, and later on for the sine and the other two inequalities can easily be extended. So, here we have used the inverse Fourier cosine transform of this g, which is given here with this square root 2 over pi, and then we can interchange this order of integration. So, this changing this order of integration in this above double integration, what we will get now, we have here g hat alpha. So, it was d alpha dx, now we have here dx d alpha. So, that is the change. So, the inner integral has now become over the x. So, we have to have the x there f x and cos alpha x, g hat c alpha was free from x. So, we have written out of this inner integral. And now, if we take a closer look, this f x cos alpha x dx, this is exactly the Fourier cosine transform of this f, which we can denote by the f c hat, and then g c hat is already there, and then we have this d alpha. So, this is how we have proved this this identity, which is for cosine transform, by the similar steps we can use for proving the identity or the Parseval's identity for the sine transform. Well, now we will do some example problems. So, the first problem here is to find the Fourier sine transform of this function e power minus x, where this x is greater than 0. And then later on, once we have this Fourier sine transform, we can find the value of this integral 0 to infinity x sine m x over 1 plus x square dx. So, let us first go with the Fourier sine transform. So, using the definition of the Fourier sine transform, which we know that e power minus x and then sine alpha x dx, that as per the definition, and let us denote this integral here by I, and so that we can solve first for this I, and later on we can multiply by this factor 2 over square root 2 over pi to get the Fourier sine transform of e power minus x. So, taking this integral as 0 to infinity e power minus x sine alpha x, we can integrate this by parts. So, this e power minus x is being integrated here with minus sine e power minus x, and then sine alpha x as it is, and then we are putting this limit 0 to infinity plus again the integration of this e power minus x. So, that minus minus will make it plus here. Then we have this alpha, which is coming because of the sine alpha x was differentiated here. So, we have the cos alpha x with this alpha term. So, now considering the first part, when x goes to infinity, this e power minus x will make this term 0, and when x goes to 0, then this sign 0 will be 0. So, the first term will disappear, and then we have from the second term alpha e power minus x cos alpha x dx. So, again we can integrate this by parts. So, we have this minus e power minus x and then cos alpha x, and again the same argument to get this result. So, finally, we get here alpha 1 minus alpha I, and this was the result of the alpha itself or I itself. So, we can bring the I to the other side, and finally, we conclude that this I is alpha over 1 plus alpha square. Having this integral done, then we can write down the Fourier sine transform of e power minus x just by multiplying by this factor 2 over square root pi, and then we have this alpha over 1 plus alpha square. So, that was the first part where we need to find the Fourier sine transform of this e power minus x function. The second is we want to evaluate this integral. So, we proceed further. So, we have the Fourier sine transform which we have just evaluated, and now we take the inverse Fourier transform. So, this is always the trick for the evaluation of the integrals, and the inverse transform says that e power minus x, because this was the function which was used to get this Fourier sine transform, and now we are applying this inverse formula. So, here Fourier sine transform of alpha which is already given there, and then sin alpha x, and then we have a d alpha term. So, this 2 over pi and then 0 to infinity, we have this f hat alpha which is alpha over 1 plus alpha square with this factor square root 2 over pi, but there was already 2 over pi square root. So, that has become now 2 over pi, and for f hat alpha now the extra term we have this alpha plus 1 plus alpha square, and then sin alpha x, and we have this d alpha term. So, now we want to evaluate this integral x sin m x over 1 plus x square dx, and if we take a closer look here, this is matching with this integral itself, having this integral over x 1 plus x square dx. Here we have alpha 1 plus alpha square d alpha, and there is a sine term also where x must be there. So, here we have the x. So, somehow for this x we are using here this alpha, and for this x we are using m there. So, if we interchange in this integral now, this alpha if we replace by x, but then this x must be replaced by some other number m. So, we can replace this x here and this x of course by m, and then this alpha which is appearing here and here, then we can replace by this x. So, replacing this x to this m and then alpha to x, what we will get, the right hand side we will have x plus 1 over x square, we have sine, and then alpha will become x and x will become m. So, m x, and then we have dx because this alpha has become now x, and the right hand side this 2 over pi can go to the other side to make it pi by 2, and we have e power minus m there. So, the value of this integral x over 1 plus x square sin m x dx is equal to pi by 2 e power minus m. So, find the Fourier transform. This is the another problem. Find the Fourier cosine transform now of e power minus x square. Now, the function is e power minus x square. So, by the definition of the Fourier cosine transform, we know that it is a f u cos alpha u. So, this f u is now e power minus u square, and this cos alpha u, and then we have du. So, here there is a difficulty now to compute this integral by parts, because e power minus u square is sitting, which is not easy to differentiate or to integrate this, and having the similar steps which we have followed in the earlier example where e power minus u was there. Now, we have e power minus u square. So, there is another trick which we can use now. So, denoting this integral as I, we can differentiate this I with respect to alpha and then see. So, when we differentiate with respect to alpha this integral, what will happen? We will get, because alpha is here in cos alpha u. So, that will become minus sin alpha u, and then one u will appear there. So, as du, and now in this new integral we can easily do, because this u will be clubbed with e power minus u square. So, that we can integrate this e power minus u square easily, and then integrating by parts, what we have d I over d alpha is equal to, we have minus half there because of this e power minus u square into u when we integrate. So, basically we need 2 u there and then 1 by 2 we can have outside. So, that will be e power minus u square, the integral of e power minus u square into 2 u, and then this sin alpha u as it is, and in the second case here the sin will become cos alpha u, and then we have this alpha from here. So, that is already there now, and e power minus u square. So, that is the result of this integration by parts. And now, looking at the first term, when this u is 0, so this sign will become 0, and when u is infinity, the e power minus u square will make it 0. So, what we have then minus alpha by 2, and then this is exactly the integral which we have started with, that is I itself. So, we have a differential equation here, d I over d alpha is equal to minus alpha by 2 I, and which can be solved now to give I is equal to c e power minus alpha square by 4. Now, the question is that what is this arbitrary constant of integration? But if we recall that I was e power minus u square cos alpha u du, and I at 0. So, this I is a function of alpha. So, if we take I at 0, then 0 to infinity we have e power minus u square, cos 0 is 1, and then we have du, and this integral we are familiar with. This, the value of this is square root pi by 2. So, we can use this I naught as square root pi by 2, which can give us this c again square root pi by 2, and putting this in the integral back, we have I square root pi by 2 e power minus. So, therefore, the desired Fourier transform is given by this equation here. So, we need to just substitute I there. So, the I is given by square root pi by 2 e power minus alpha square. So, just by substituting we got the Fourier coefficient of e power minus x square. So, we have another example, and this is the last example of this lecture. Using this Parseval's identity, we will prove that this integral 0 to infinity dt over a square plus t square into b square plus t square is equal to pi over 2 a b and a plus b. So, here we have to consider these two functions f x e power minus x and then g x e power minus b x. A similar example we have done for computing Fourier cosine transform of e power minus x, and this will follow the similar steps. So, the Fourier cosine transform of f will be given by this formula e power minus a x and then cos alpha x dx, and then integrating by parts we can end up with square root 2 over pi a over a square and plus alpha square. Similarly, for g x, because the only difference is that instead of a we have b. So, the Fourier cosine transform of g can be similarly obtained as square root 2 over pi and b over b square plus alpha square. So, having these two Fourier cosine transforms for f and g, we can now apply the Parseval's identity. So, just to recall, so the Parseval's identity was the multiplication of the Fourier cosine transform when integrated over 0 to infinity. The value is equal to the integral when the two functions are multiplied and integrated over 0 to infinity. So, we have this information now, the Fourier cosine transform of alpha and Fourier cosine transform of this f and g. So, we can substitute there, and the right hand side, because the function was the exponential minus a x and exponential minus b x. So, that can be clubbed now and it can easily be integrated. So, now e power minus a plus b x, that the integration will give e power minus a plus b x over a plus b, and then the limits we have 0 and infinity. So, by substituting this e power infinity, this e power a plus b x will go to 0, and then we have for 0 1 over a plus 1 over a plus b when we substitute this value 0, and then there is a factor 2 a b over pi sitting to the left hand side, which will contribute here to pi over 2 a b, and then we have 1 over a plus b coming from this limit there. So, in this way we have easily computed this integral using this Parseval's identity, and here these are the references used for preparing this lecture. And just to conclude, that we have discussed today the Fourier cosine transform of a function f, which is given by this formula having this f u and cos alpha u in its integrand, and its inverse Fourier cosine transform can be obtained. So, if we substitute this f c alpha there in the formula and multiplied by cos alpha x, after this integration we can get back to f x again, and this is called inverse Fourier cosine transform. Similarly, we have Fourier sine transform, and Fourier sine transform, instead of this cos we will have sine there, and here also this cos will be taken as sine alpha x d alpha. We have also discussed the Parseval's identity, and its application was also demonstrated for evaluating integral. So, here this product of the Fourier cosine transform when integrated over 0 to alpha, the value is equal to the product of f and g integrated over 0 to infinity, and the same result we have for Fourier sine transform. So, that is all for this lecture, and I thank you for your attention.